Hello there, and welcome to the Sleepy Library. Tonight, we are floating into the gentle realm of clouds, where water and air come together to paint the sky with forms both familiar and mysterious. Clouds are the softest architecture of our atmosphere, shifting shapes that dance above us every day without asking for notice. They are made of the most delicate material, tiny droplets of water or ice crystals so small that the weakest breeze keeps them aloft. Yet together, these countless particles gather into structures that can span hundreds of miles and reshape our weather, our light, and the very temperature of our planet. This is not just a journey through the science of condensation. It is a journey through wonder, into the quiet poetry of water suspended in air. The things we will discover tonight are not only beautiful, but profoundly essential to life itself. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the evening settle around you and allow your mind to soften. Let's begin. Clouds are made of water droplets so small that millions could fit in a single raindrop. Each droplet measures only 10 to 15 microns across, which is smaller than the width of a human hair. These particles are so lightweight that even the gentlest upward movement of air can keep them floating indefinitely. They cluster together in numbers beyond counting, forming the white masses we see above. Yet each droplet began as a single molecule of water vapor that found a tiny speck of dust, salt, or pollen to cling to. Without these microscopic particles acting as seeds, water vapor would struggle to condense at all. The air is full of these invisible nuclei, drifting on currents we cannot see, waiting for the right moment of temperature and moisture to become the foundation of a cloud. In this way, clouds are partnerships between water and dust, between the visible and the hidden, between what falls from the sky and what rises from the earth. There are 10 basic types of clouds recognized by meteorologists worldwide. These classifications were first organized in 1802 by an English pharmacist named Luke Howard, who watched the sky with careful attention and noticed that clouds appeared in repeating forms. He borrowed from Latin to give them names that described their shapes and behaviors. Cirrus for curls of ice high in the atmosphere, cumulus for heaps that rise like towers, stratus for layers that spread like blankets, nimbus for those that bring rain. Over time, his simple system grew more detailed, expanding to include combinations and variations, but the core categories remain. Today, when meteorologists look up, they still use Howard's language. Cirrus, cirrocumulus, cirrostratus at high altitudes. Altocumulus and altostratus in the middle ranges. Stratocumulus, stratus, nimbostratus, cumulus, and cumulonimbus closer to the ground. Each type tells a story about temperature, humidity, and the invisible motions of air that shaped it. The sky is a library of forms, and clouds are its changing words. High clouds form where the air is coldest and thinnest. At altitudes above 20,000 feet, temperatures plunge so low that water cannot remain liquid. Instead, it freezes instantly into ice crystals that catch the light and shimmer in the sun. Cirrus clouds are made entirely of these crystals, thin and wispy, trailing across the sky like brushstrokes. They move with high-altitude winds that can exceed 100 miles per hour. Yet from the ground, they appear to drift slowly, almost motionless. Cirrocumulus clouds form small patches of white, rippled like sand on a beach, while cirrostratus spreads in pale sheets that often create halos around the sun or moon. These halos occur when light bends through the ice crystals, refracting in specific angles that paint rings of soft color in the sky. High clouds rarely produce rain because the ice crystals are too small and too scattered to fall far before evaporating. But they serve as messengers. Their arrival often signals a change in weather, as warm fronts approaching from the distance push moisture higher into the atmosphere. Middle clouds occupy the space between 6,000 and 20,000 feet above the ground. Here, the air is still cool, but not as extreme as the heights above. These clouds can be made of water droplets, ice crystals, or a mixture of both, depending on the season and location. Altocumulus clouds appear as puffy grey or white masses, often arranged in rows or waves that ripple across the sky. They form when moist air rises and cools just enough to condense, but not enough to build into towering structures. Altostratus clouds spread in uniform grey or blue sheets, thick enough to dim the sun, but thin enough to reveal its position as a blurred glow. These clouds often precede steady rain or snow, especially when they thicken and lower over time. Nimbostratus clouds also form in this range, dark and heavy, producing continuous precipitation that can last for hours or even days. Unlike dramatic thunderstorms, nimbostratus rain falls gently, soaking the ground without violence. It is the rain of autumn afternoons and quiet winter mornings, the kind that makes you want to stay indoors and listen. Low clouds hug closer to the earth, forming within the first 6,000 feet of the atmosphere. These are the clouds we know most intimately because they often touch the ground as fog. Stratus clouds create flat, featureless layers of grey that can cover the entire sky, blocking the sun and casting a soft, even light across the landscape. They form when stable air near the surface becomes saturated with moisture, unable to rise but too heavy with water to remain invisible. Stratocumulus clouds combine the layered nature of stratus with the puffy texture of cumulus, forming low rolls or patches that often appear at dawn or dusk. Cumulus clouds are the classic puffs of white we draw as children, with flat bases and rounded tops that rise like cauliflower. They form when warm air near the ground heats up and rises, carrying moisture upward until it cools enough to condense. On calm days, cumulus clouds drift gently, small and scattered. But when conditions are right, they can grow vertically into towering structures that reach tens of thousands of feet into the sky. Cumulonimbus clouds are the giants of the atmosphere. These are the thunderstorm clouds, rising from low altitudes all the way to the top of the troposphere, sometimes exceeding 60,000 feet in height. They form when unstable air rises rapidly, pulling moisture upward in powerful updrafts that can exceed 100 miles per hour. As the cloud grows, its top flattens into an anvil shape, spreading out against the boundary where the troposphere meets the stratosphere. Inside, water droplets freeze and collide, generating static electricity that builds until it releases as lightning. Thunder follows as the air around the lightning channel heats and expands in an instant, creating shock waves that rumble across the sky. Cumulonimbus clouds produce heavy rain, hail, strong winds, and sometimes tornadoes. Yet even in their violence, they serve a purpose. They transport heat from the surface to the upper atmosphere, helping to balance temperatures across the planet. They are engines of energy, transforming the sun's warmth into motion, sound, and light. Clouds form when air rises and cools to its saturation point. The atmosphere holds water vapor invisibly, mixed with nitrogen, oxygen, and other gases. But the amount of water vapor air can hold depends on temperature. Warm air can carry more moisture than cold air. When air rises, whether pushed by a mountain, lifted by a weather front, or heated by the sun warming the ground, it expands and cools. As it cools, it reaches a point called the dew point, where it can no longer hold all its moisture. The excess water vapor condenses onto tiny particles floating in the air, forming droplets or ice crystals. This process happens continuously in the atmosphere, wherever conditions allow. Mountains force air upward, creating clouds that cling to peaks. Warm fronts lift cooler air, creating broad layers of clouds. Heated ground sends columns of air rising, forming cumulus clouds that mark invisible thermals. Even the meeting of different air masses can trigger condensation. The sky is a constant ballet of rising and falling air, and clouds are the visible signs of these movements. Fog is simply a cloud that touches the ground. It forms under the same conditions as other clouds, when air becomes saturated and water vapor condenses. But instead of forming high above, fog develops when cool air near the surface cannot hold its moisture. Radiation fog forms on clear, calm nights when the ground loses heat and cools. The air directly above it. This is the fog that fills valleys at dawn, sitting like a soft blanket until the sun warms the air enough to evaporate it. Advection fog forms when warm, moist air moves over a cooler surface, such as when ocean air drifts over cold water or snow-covered land. This fog can be thick and persistent, lasting for days until the wind shifts. Upslope fog forms when air climbs a mountain or hillside, cooling as it rises. It clings to slopes and ridges, shrouding forests in mist. Fog transforms familiar landscapes into mysterious places where sounds are muffled and distances become uncertain. It is the atmosphere at its most intimate, wrapping around us rather than floating above. Clouds reflect sunlight back into space, helping to cool the earth. The white surfaces of clouds act like mirrors, bouncing solar energy away before it can warm the ground. This reflective quality, called albedo, is especially strong in thick, low clouds like stratocumulus. Scientists estimate that clouds reflect about 30 to 60% of the sunlight that strikes them. Over the oceans, where these clouds are most common, this reflection prevents a significant amount of heat from reaching the water. Without clouds, the Earth would absorb more solar energy and warm considerably. This cooling effect is one reason why cloudy days feel cooler than sunny ones. The clouds act as shields, softening the sun's intensity and casting diffuse light across the land. Yet the relationship is not simple. While clouds cool the planet during the day, they also trap heat at night, acting like blankets that slow the escape of warmth into space. This dual nature makes clouds one of the most important and complex factors in our climate system. High clouds trap heat and warm the planet. Unlike low clouds that reflect sunlight, thin cirrus clouds allow most of the sun's rays to pass through to the Earth. But when the ground radiates heat back towards space as infrared energy, these high ice clouds absorb it and re-radiate some of it back down. This process traps warmth in the atmosphere, similar to how greenhouse gases work. Because cirrus clouds are so cold, they emit very little heat upward into space, which means more energy stays below. The net effect of cirrus clouds is warming, unlike most other cloud types that have a cooling influence. This makes cirrus clouds particularly important in discussions of climate change. As the atmosphere warms, some scientists predict that cirrus clouds may become more common, which could amplify warming even further. Others suggest that cloud patterns may shift in ways that increase cooling clouds instead. The balance between these effects remains one of the greatest uncertainties in climate science. Clouds hold tremendous power over our planet's temperature, yet their behavior is difficult to predict. Clouds are essential to the water cycle. Water evaporates from oceans, lakes, rivers, and soil, rising into the atmosphere in visible vapor. Plants also release water through their leaves in a process called transpiration. Once in the air, this vapor travels with the wind, sometimes for hundreds of miles, until it encounters conditions that cause it to condense into clouds. These clouds eventually release the water as precipitation, rain, snow, sleet, or hail, returning it to the surface where it flows into streams, soaks into the ground, or evaporates again. Without clouds, this cycle would be incomplete. Water vapor might rise into the atmosphere, but it would struggle to condense and fall back down. The land would dry out, plants would wither, and fresh water would become scarce. Clouds are the bridges in this cycle, the vessels that carry water from one place to another, from ocean to mountain, from desert to forest. They are not just weather, they are part of the system that sustains all living things. Some clouds produce rain that never reaches the ground. These streaks of precipitation are called virga, visible as wisps or curtains that hang beneath a cloud but fade before touching the earth. Virga occurs when raindrops or ice crystals fall from the cloud base into air that is too dry or too warm. As they descend, they evaporate, turning back into vapor before they can complete their journey. From a distance, virga looks like soft grey veils trailing beneath the cloud, sometimes straight, sometimes curved by wind. It is most common in arid regions where the lower atmosphere is particularly dry, and in high-altitude clouds where the distance to the ground is great. Virga may seem like wasted rain, but it plays a role in the atmosphere. The evaporation cools the air below the cloud, which can trigger downdrafts and change local wind patterns. It also adds moisture back into the air, priming the atmosphere for future clouds and storms. Virga is a reminder that not all precipitation completes its cycle in a single fall. Sometimes water rises and falls multiple times before finally reaching the surface. Lenticular clouds look like flying saucers. These smooth, lens-shaped clouds form over mountains when stable, moist air flows over a peak and creates a series of standing waves on the downwind side. As the air rises in each wave crest, it cools and condenses, forming a cloud. As it descends into the trough, it warms and the cloud evaporates. The result is a stationary cloud that hovers in place, even as wind flows through it continuously. Lenticular clouds can stack in layers, creating formations that resemble a tower of plates or a fleet of spacecraft. They are most common in mountainous regions where strong winds blow perpendicular to ridges. Pilots avoid them because they mark areas of severe turbulence, but photographers seek them out for their striking, otherworldly appearance. These clouds often glow with vibrant colors at sunrise or sunset, and they can display iridescence when the sun illuminates them from certain angles. Lenticular clouds are proof that even the invisible currents of air can be made visible, transformed into shapes that seem too perfect to be real. Mammatus clouds appear as bulging pouches hanging from the base of a cloud. These rounded protrusions look like the underside of a quilt, soft and dimpled, or like clusters of bubbles suspended in the sky. They form when pockets of cold air sink below the cloud base, creating downward bulges that contrast with the usual flat bottom of clouds. Mammatus are most often associated with severe thunderstorms, appearing beneath the anvil of cumulonimbus clouds after the storm's peak intensity. They signal that the storm is dissipating, with sinking air replacing the strong updrafts. Despite their ominous appearance, mammatus clouds themselves are not dangerous. They do not produce tornadoes or extreme weather, but their presence indicates that powerful forces are at work in the atmosphere, and they often appear during or shortly after intense storms. The sight of mammatus clouds at sunset is particularly stunning, with the pouches catching the light in shades of pink, orange, and gold, creating a landscape in the sky that feels both soft and surreal. Noctilucent clouds are the highest clouds in Earth's atmosphere. They form in the mesosphere, about 50 miles above the surface, far higher than any weather cloud. At these extreme altitudes, temperatures drop to -230 degrees Fahrenheit, cold enough to freeze the tiny amounts of water vapor present. Noctilucent clouds are made of ice crystals so small they scatter light in a bluish glow. They are only visible during twilight, when the sun is below the horizon, but still illuminates the mesosphere from below. To an observer on the ground, they appear as luminous, silver-blue streaks across the darkening sky, glowing against the fading light. Noctilucent clouds are most common in polar regions during summer months, but they have been appearing more frequently at lower latitudes in recent decades. Some scientists believe this increase may be linked to changes in the upper atmosphere, possibly influenced by rising greenhouse gases or increased water vapor from methane oxidation. These clouds are a reminder that the atmosphere extends far beyond the weather we experience, reaching into the edge of space, where conditions are so extreme that even clouds become rare and strange. Clouds can display brilliant colors called iridescence. When sunlight passes through a thin cloud containing water droplets or ice crystals of similar size, the light is diffracted, bending and spreading into its component colors. The result is patches or bands of pastel hues, green, pink, blue, and violet, shimmering near the edge of the cloud. Iridescence is most common in altocumulus, cirrocumulus, and lenticular clouds, especially when they are thin and the droplets are uniform. The colors are often subtle and fleeting, changing as the cloud moves and the angle of sunlight shifts. Sometimes, iridescence is so vivid that it resembles the colors of an oil slick or the interior of a seashell. This phenomenon is delicate and easily missed unless you know to look for it. It appears most often near the sun, but looking directly at the sun can obscure the effect, so it's best to shield your eyes or observe the cloud when it's slightly away from the sun's glare. Iridescent clouds are nature's gentle rainbows, painted not in a single arc, but across the scattered canvas of the sky. Clouds create halos around the sun and moon. When light passes through the ice crystals in cirrostratus clouds, it refracts at specific angles, bending in ways that create rings of light. The most common halo is a circle with a radius of 22 degrees from the sun or moon, appearing as a faint white or colored ring. Sometimes a larger ring appears at 46 degrees. These halos are caused by the hexagonal shape of ice crystals, which bend light in precise, predictable ways. Occasionally, bright spots called sundogs or parhelia appear on either side of the halo, glowing with warm colors. These occur when flat, plate-like ice crystals drift horizontally through the air, acting like tiny prisms that concentrate light. Halos and sundogs are signs that high, thin clouds are present, often indicating that weather is changing. Folk wisdom says that a ring around the moon means rain is coming, and there is truth to this. The cirrostratus clouds that cause halos often arrive ahead of warm fronts, which can bring precipitation within 24 to 48 hours. The sky uses light itself to signal what is ahead. Clouds change color at sunrise and sunset. During the day, clouds appear white, because water droplets scatter all wavelengths of sunlight equally, mixing them back into white light. But when the sun is low on the horizon, its light must travel through more atmosphere to reach the clouds. As it passes through the air, shorter wavelengths like blue and violet are scattered away, leaving longer wavelengths like red, orange, and yellow to continue onward. These warm colors illuminate the clouds from below or from the side, painting them in shades that shift from pale peach to deep crimson as the sun sinks lower. High clouds like cirrus and altocumulus catch the last light of day first, glowing long after the sun has set for observers on the ground. Low clouds near the horizon often appear darker, silhouetted against the brighter sky. The colors deepen and fade in a slow progression, a daily performance that changes with the season, the weather, and the amount of dust or pollution in the air. Sunsets and sunrises are not just beautiful. They are lessons in light, refraction, and the physics of atmosphere. Some clouds form in the wake of airplanes. Contrails, short for condensation trails, appear when hot, moist exhaust from jet engines mixes with the cold air of the upper atmosphere. The water vapor in the exhaust condenses instantly, forming a line of ice crystals that marks the plane's path. Contrails can be short-lived, evaporating within seconds if the air is dry. But in humid conditions, they can persist for hours, spreading and merging with other contrails to form thin sheets of cirrus. These artificial clouds can cover significant portions of the sky, especially over busy flight corridors. Some research suggests that contrails have a warming effect on the climate because they trap heat like natural cirrus clouds, though their impact is smaller than that of greenhouse gases. Contrails are a visible reminder of human influence on the atmosphere, a mark we leave in the sky that fades but does not disappear entirely. They blur the line between natural and artificial, showing how even our movements high above the ground can alter the fabric of the sky. Clouds help moderate temperatures at night. On clear nights, heat radiates from the Earth's surface into space, causing temperatures to drop quickly. This is why deserts, which often have clear skies, experience drastic temperature swings between day and night. But when clouds are present, they absorb some of the outgoing heat and re-radiate it back toward the ground, acting like a blanket that slows cooling. The thicker and lower the clouds, the more effective they are at trapping warmth. Overcast nights are typically warmer than clear nights, sometimes by 10 or 20 degrees. This insulating effect is especially important in winter, when cloudy conditions can prevent frost from forming and protect crops and plants from freezing. It also explains why cloudy winters feel milder than clear ones, even if the daytime temperatures are similar. Clouds do not generate heat. They simply redistribute it, slowing the exchange of energy between the ground and space. In this way, they act as regulators, smoothing out the extremes of temperature that would otherwise make the Earth a harsher place. Cloud cover varies around the world. Some regions are nearly always cloudy, while others see clear skies for most of the year. The Southern Ocean surrounding Antarctica is one of the cloudiest places on Earth, with marine stratocumulus covering the water for much of the year. Equatorial regions also have high cloud cover, especially over rainforests and oceans, where warm, moist air rises continuously. Deserts, by contrast, have some of the lowest cloud cover on the planet. The dry air and stable atmospheric conditions prevent moisture from condensing. Subtropical regions, where high-pressure systems dominate, also tend to have clear skies. Cloud patterns shift with the seasons as weather systems move and moisture sources change. Understanding these patterns helps scientists predict how clouds might change in a warming climate. If cloud cover increases in regions that are currently clear, it could provide a cooling effect. But if clouds decrease in areas that are now cloudy, it could accelerate warming. These shifts are difficult to predict because clouds are influenced by so many factors, from ocean temperatures to wind patterns to the amount of aerosols in the air. Clouds exist on other planets. Earth is not the only world with clouds, though ours are unique in being made almost entirely of water. Venus has thick clouds of sulfuric acid that completely obscure its surface, creating a runaway greenhouse effect that makes the planet the hottest in the solar system. Mars has wispy clouds of water ice and carbon dioxide, much thinner than Earth's, visible in the early morning or around the poles. Jupiter and Saturn have bands of clouds made of ammonia and other chemicals, swirling in storms that can last for centuries. Titan, Saturn's largest moon, has clouds of liquid methane that produce rainfall, filling lakes and rivers on its frozen surface. Even distant exoplanets have been observed with cloud features, detected through changes in the light they reflect or emit. These clouds are not like ours. They may be made of molten rock vapor on hot Jupiters, or ices of exotic compounds on cold worlds far from their stars. But the basic process is the same. When a gas cools below its condensation point, it forms droplets or crystals that cluster together. Clouds are not unique to Earth. They are a universal phenomenon, appearing wherever atmospheres exist. Morning glory clouds are rare rolling tubes that stretch for hundreds of miles. These remarkable formations occur most famously in northern Australia, particularly over the Gulf of Carpentaria, though they have been observed in other parts of the world as well. A morning glory cloud is a solitary roll cloud, a horizontal cylinder that moves forward like a wave rolling across the sky. It can be up to 600 miles long and travel at speeds of 35 miles per hour. The cloud itself is smooth and dark, often appearing in the early morning hours, hence the name. Despite decades of study, scientists are still not entirely certain what causes these clouds. They seem to form when colliding sea breezes create a wave in the atmosphere, which then propagates inland. Glider pilots seek out morning glory clouds because the rolling motion creates powerful updrafts that can carry aircraft aloft. To see one is to witness one of the sky's rarest performances, a cloud shaped not like a puff or a layer, but like a living, moving river in the air. Aspiratus clouds look like an upside-down ocean. These turbulent formations were only officially recognized as a distinct cloud type in recent years, added to the International Cloud Atlas in 2017. Aspiratus clouds appear as chaotic, undulating waves that ripple across the underside of a cloud layer, creating the impression of a stormy sea turned on its head. The texture is rough and dramatic, with peaks and troughs that seem to churn and lock, though the cloud itself moves slowly. They form in conditions where the atmosphere is unstable at certain altitudes, causing air to mix and churn in complex patterns. Despite their ominous appearance, aspiratus clouds rarely produce severe weather. They are more spectacle than threat, though they can occur near thunderstorms. Their discovery reminds us that even after centuries of studying the sky, there are still patterns we have not fully documented, still forms we are learning to name. The sky is not static. It is constantly revealing new textures and shapes, inviting us to keep watching. Kelvin-Helmholtz clouds resemble ocean waves breaking in the sky. These beautiful formations occur when two layers of air move at different speeds, creating a shear between them. The faster layer on top slides over the slower layer below, and if the conditions are just right, the boundary between them becomes unstable. It begins to ripple, forming curls and crests that look like waves about to crash. Kelvin-Helmholtz clouds are rare and short-lived, usually lasting only a few minutes before dissipating. They are most often seen in cirrus or altocumulus layers, though they can form at any altitude where wind shear exists. The effect is named after physicists Lord Kelvin and Hermann von Helmholtz, who studied the instability that causes it. Pilots avoid these clouds because they mark areas of severe turbulence, but for those on the ground, they are a visual delight. To see the sky behaving like water, to watch clouds curl and break as if they were part of the ocean, is to be reminded that air is a fluid too, subject to the same forces of motion and gravity. Hole-punch clouds are circular gaps in a layer of altocumulus or cirrocumulus. These strange formations occur when a portion of the cloud suddenly turns to ice, causing the crystals to grow rapidly and fall out, leaving a clear hole behind. The process is called the Bergeron-Feindeisen process, where ice crystals grow at the expense of water droplets in a supercooled cloud. Once started, the effect can spread, creating larger holes or even entire canals of clear sky. The falling ice appears as virga beneath the hole, trailing down in streaks or wisps. Hole-punch clouds are often triggered by aircraft passing through the cloud layer. The turbulence and exhaust from the plane can introduce ice nuclei that seed the cloud, starting the chain reaction. These clouds are sometimes mistaken for unusual phenomena because of their sharp, geometric appearance. But they are entirely natural, a result of the delicate balance between water and ice in cold clouds. They show how a small disturbance can create a dramatic effect, how the right nudge can unzip an entire layer of sky. Clouds have inspired art, poetry, and philosophy for centuries. People have always looked up and seen more than water vapor. They see shapes, faces, dragons, castles, entire worlds that shift and dissolve. Medieval artists painted them as the thrones of heaven, soft and golden. Romantic poets wrote of them as symbols of change and impermanence, of the fleeting nature of beauty. In Chinese and Japanese art, clouds are rendered as stylized swirls, representing the boundary between earth and sky, between the mortal and the divine. Modern artists continue to find inspiration in clouds, capturing their light and texture in paintings, photographs, and digital art. Clouds are democratic in their beauty. They appear to everyone, rich or poor, in every country and every age. They cost nothing to observe and require no special knowledge to appreciate. Yet, they are endlessly varied, never repeating the same form twice. In a world that often feels fixed and rigid, clouds remind us that change is natural, that softness has strength, that the sky is a canvas constantly repainting itself. Clouds can produce sounds, though we rarely hear them directly. Thunder is the most obvious example, the shockwave created when lightning heats the air to extreme temperatures. But clouds themselves can be noisy in ways we do not usually notice. Inside a cumulonimbus cloud, the roar of wind and the collision of ice particles create a constant rumble that would be deafening if we could hear it from inside. Rain falling from clouds makes sound when it strikes surfaces, leaves, roofs, water. Each drop is a tiny percussion instrument. In fog, sound behaves differently. It is muffled and distorted, traveling shorter distances and bending in unexpected ways. This happens because water droplets absorb and scatter sound waves, dampening them before they can travel far. Sailors have long known that foghorns must be loud and low-pitched to penetrate the mist. Clouds also affect how we hear distant sounds. A low cloud layer can trap sound waves near the ground, making faraway noises seem closer. Clouds shape not just what we see, but what we hear, altering the acoustic landscape of the world. Some clouds glow at night. Nacreous clouds, also called mother-of-pearl clouds, form in the stratosphere at altitudes of 50,000 to 80,000 feet. They appear most often in polar regions during winter, when the stratosphere is cold enough to support cloud formation. These clouds are made of tiny ice crystals that scatter light in brilliant iridescent colors: greens, pinks, blues, purples. They glow brightest just after sunset or before sunrise, when the sun is below the horizon for observers on the ground, but still illuminates the stratosphere. Nacreous clouds are rare and beautiful, but they are also a sign of stratospheric disturbance. They form in extremely cold conditions, and their presence can indicate unusual weather patterns or the breakdown of the polar vortex. Some scientists also study them because they play a role in ozone chemistry. The surfaces of ice crystals in nacreous clouds provide sites for chemical reactions that can accelerate the destruction of ozone, contributing to the ozone hole over Antarctica. These clouds are both art and science, beauty with consequences. Clouds can last for seconds or for days. Some clouds are transient, forming and dissipating in minutes. Small cumulus clouds on a summer afternoon might bubble up, last for a few moments, and then evaporate as the air sinks and warms. Contrails can vanish almost as quickly as they form. But other clouds are remarkably persistent. Stratus and stratocumulus layers can cover the sky for days at a time, especially in coastal regions where marine air provides a steady supply of moisture. Nimbostratus clouds that accompany slow-moving weather systems can produce rain for hours or even days without breaking. The lifespan of a cloud depends on the supply of moisture, the stability of the air, and the strength of the processes that created it. Even within a single cloud, different parts may be forming and evaporating continuously, so that the cloud as a whole appears stable, even though its individual droplets are constantly cycling. This dynamic balance is one of the reasons clouds are so hard to model in climate simulations. They are not static objects, they are processes, ever-changing and responsive to the smallest shifts in temperature, humidity, and wind. Clouds have been used for navigation and weather prediction for thousands of years. Sailors learned to read the sky long before meteorology became a science. Cirrus clouds arriving from the west often meant a storm was approaching. Mary's tails, the wispy streaks of cirrus, were a sign of strong winds aloft. A halo around the moon suggested rain within a day or two. Puffy cumulus clouds in the morning indicated fair weather, while towering cumulus later in the day warned of possible thunderstorms. Indigenous peoples around the world developed their own systems of cloud reading, tailored to their local climates and seasons. Farmers watched the clouds to decide when to plant and when to harvest. Fishermen gauged the safety of going out to sea by the color and movement of clouds on the horizon. These observations were passed down through generations, becoming part of folk wisdom. Even today, in an age of satellites and computer models, knowing how to read clouds can provide valuable information. The sky still speaks if we know how to listen. Cloud seeding is a technique used to encourage precipitation. It involves introducing particles, usually silver iodide or salt, into clouds to provide additional nuclei for water droplets or ice crystals to form around. The idea is to enhance the natural process of precipitation, either by stimulating rain to fall or by reducing the size of hailstones. Cloud seeding has been used since the mid-20th century, with varying degrees of success. Some studies suggest it can increase rainfall by 5 to 15% in certain conditions, particularly in mountainous regions where clouds are already near the point of releasing precipitation. Other research questions whether the effects are significant enough to justify the cost. Cloud seeding is used in some regions to augment water supplies during droughts, or to reduce the intensity of storms. It has also been used to clear fog at airports, but it is not a cure-all. Seeding only works if the right type of clouds are present, and even then, the results are difficult to measure because weather is naturally variable. You cannot easily prove that rain fell because of seeding rather than natural causes. The technique remains a tool, useful in some situations, but limited in others. The weight of all the water in the atmosphere is staggering. If you could gather all the water vapor in the air at any given moment, it would weigh about 12 trillion metric tons. That is roughly equivalent to the weight of 50,000 aircraft carriers. Yet this water is so dispersed that we do not feel its weight. It is dissolved in the air, spread over the entire surface of the planet. When this vapor condenses into clouds, the weight does not change, but it becomes concentrated into smaller volumes. A single cumulus cloud, one of those small, fluffy clouds on a summer day, can weigh more than 1,000,000 pounds. A large cumulonimbus cloud, the kind that produces thunderstorms, can contain hundreds of millions of pounds of water. Yet these clouds float because the water is distributed among countless tiny droplets, each so small that the gentlest updraft keeps it aloft. The cloud as a whole is denser than the surrounding air, but the droplets themselves are light enough to remain suspended. If the droplets grow large enough, they fall as rain. The cloud releases its weight back to the earth, and the cycle begins again. Clouds affect aircraft in many ways. Pilots must navigate around or through clouds depending on the type. Cumulus clouds mark areas of rising air, which can cause turbulence, but also provide lift for gliders. Cumulonimbus clouds are dangerous and must be avoided. The powerful updrafts and downdrafts inside a thunderstorm can toss an aircraft violently, and the presence of ice, lightning, and hail adds further risk. Stratus and fog can reduce visibility to zero, making takeoff and landing difficult or impossible without instruments. High cirrus clouds are usually benign, though they can indicate turbulence at jet altitudes. Icing is a constant concern for pilots. When an aircraft flies through a cloud where temperatures are below freezing but water droplets remain liquid, those droplets can freeze on contact with the aircraft's surface, building up layers of ice that add weight and disrupt airflow. Modern aircraft have systems to detect and remove ice, but it remains a serious hazard. Despite these challenges, clouds also help pilots. Cloud formations can indicate weather patterns, wind direction, and the location of fronts. Experienced pilots learn to read clouds as a supplement to weather forecasts and instruments. Clouds play a role in the global energy budget. Every day, the Earth absorbs energy from the sun and radiates energy back into space. The balance between these two processes determines the planet's temperature. Clouds influence both sides of this equation. By reflecting sunlight, they reduce the amount of energy absorbed. By trapping infrared radiation, they reduce the amount of energy lost. The net effect depends on the type, altitude, thickness, and distribution of clouds. Low, thick clouds tend to cool the planet because they reflect more light than they trap heat. High, thin clouds tend to warm it because they allow light through but trap outgoing heat. On average, clouds have a slight cooling effect, reducing global temperatures by a few degrees Celsius compared to a cloudless Earth. But this balance is delicate. Changes in cloud cover, whether from natural variability or human influence, can shift the energy budget. This is why clouds are central to climate science. They are one of the main uncertainties in predicting how much the planet will warm in response to increasing greenhouse gases. Small changes in cloudiness can have large effects on temperature. Cloud formation is influenced by aerosols, tiny particles suspended in the air. These particles can be natural, such as sea salt, dust, pollen, or volcanic ash, or they can come from human activities, such as pollution from vehicles, factories, and fires. Aerosols act as cloud condensation nuclei, providing surfaces for water vapor to condense onto. Without them, clouds would struggle to form. But the relationship is complex. More aerosols generally mean more cloud droplets. But those droplets are smaller because the same amount of water is divided among more particles. Smaller droplets make clouds more reflective, which can have a cooling effect on the climate. This is called the indirect aerosol effect, or the cloud albedo effect. However, aerosols can also absorb sunlight and heat the atmosphere, which can inhibit cloud formation in some cases. Pollution has increased the number of aerosols in the atmosphere, and this has likely changed cloud properties in ways that are still being studied. Some research suggests that aerosol pollution has masked some of the warming from greenhouse gases by making clouds more reflective. As air quality improves and aerosol concentrations decrease, this masking effect may diminish, leading to faster warming. Clouds can produce optical phenomena called coronas. When the moon or sun is seen through a thin cloud, it may appear surrounded by one or more colored rings. These are not halos, which are caused by ice crystals. Coronas are caused by diffraction, the bending of light waves around water droplets. The size of the corona depends on the size of the droplets. Smaller droplets produce larger coronas, and vice versa. The colors are usually pastel, with blue on the inside and red on the outside, though the pattern can repeat in multiple rings. Coronas are most visible when the cloud is thin and uniform, with droplets of similar size throughout. They are common around the moon because it is easier to look at than the sun. Watching a corona form and shift as a cloud passes over the moon is a subtle and meditative experience. The colors pulse and change, sometimes brightening, sometimes fading, depending on the thickness and texture of the cloud. It is a reminder that light is a wave, and that the smallest particles can bend and shape it in beautiful ways. Clouds are continuously monitored by satellites. Since the 1960s, weather satellites have provided a view of clouds from above, allowing meteorologists to track storms, measure cloud cover, and observe patterns on a global scale. Early satellites used visible light cameras, capturing images similar to what you would see from an airplane. Later satellites added infrared sensors, which detect heat and allow clouds to be observed at night or through other clouds. Modern satellites carry a suite of instruments that measure cloud properties in multiple wavelengths, from ultraviolet to microwave. These measurements can reveal cloud height, temperature, thickness, particle size, and even whether the cloud is made of water or ice. Satellites can also track the motion of clouds, providing data on wind speed and direction at different altitudes. This information is fed into weather models, helping forecasters predict storms, temperature changes, and precipitation. Satellite data has revolutionized meteorology, making forecasts more accurate and giving us a perspective on clouds that was impossible from the ground alone. The view from space shows clouds not as isolated formations, but as interconnected systems that span continents and oceans. Thunderstorms can produce clouds that glow with lightning. From a distance, a thunderstorm at night can look like a flickering lantern, with flashes of light illuminating the cloud from within. This is because lightning occurs inside the cloud as well as between the cloud and the ground. Most lightning, in fact, never reaches the surface. It arcs between different regions of charge within the cloud, heating the air and creating the bright flashes we see. When lightning occurs inside a dense cloud, the light diffuses through the water droplets and ice crystals, creating a soft glow that spreads across the entire cloud mass. This is sometimes called sheet lightning, though it is the same phenomenon as ordinary lightning, just hidden from direct view. Watching a distant thunderstorm pulse with light is one of the most mesmerizing experiences in nature. The cloud becomes a living thing, breathing with energy, illuminating itself against the dark sky. It is a reminder that clouds are not just passive accumulations of water. They are arenas of immense energy, where electricity builds and discharges in pulses of light and sound. Pyrocumulus clouds form above wildfires and volcanic eruptions. These clouds are generated by intense heat rising from below, carrying ash, smoke, and moisture upward into the atmosphere. As the hot air rises, it cools and condenses, forming a cloud above the heat source. Pyrocumulus can grow into full cumulonimbus clouds, complete with lightning and precipitation, even in areas that would not normally support thunderstorms. The rain that falls from these clouds can help suppress the fire below, though it is often accompanied by strong winds that can spread the flames. Volcanic eruptions produce similar clouds, but the material is different. Instead of smoke, the cloud contains volcanic ash, sulfur dioxide, and other gases. These volcanic clouds can rise tens of miles into the stratosphere, where they spread across the globe and affect climate. The eruption of Mount Pinatubo in 1991, for example, injected so much material into the stratosphere that it cooled global temperatures by about 0.5 degrees Celsius for several years. Pyrocumulus and volcanic clouds are reminders that clouds are not always formed by weather. They can be created by forces from below, by fire and upheaval, by the restless energy of the earth itself. Clouds influence the colors of twilight. The deep reds and purples that paint the sky after sunset are caused by light scattering through the atmosphere, but clouds amplify and shape these colors. High clouds catch the last rays of sunlight long after it has set for observers on the ground, glowing in shades of orange, pink, and crimson. The underside of low clouds may appear dark and silhouetted, creating contrast against the brighter sky. The most vivid twilights occur when the lower atmosphere is clear, but high clouds are present. The clean air allows light to penetrate without excessive scattering, while the high clouds act as screens that catch and reflect the light. Dust and pollution can also enhance twilight colors by scattering more light, though the effect is usually to mute the colors at ground level while intensifying them aloft. After major volcanic eruptions, twilights around the world become more vibrant for months or even years, as particles in the stratosphere scatter light in new ways. The beauty of twilight is a collaboration between air, light, and water, a daily farewell performed by the sky. Cloud streets are parallel rows of cumulus clouds. These formations occur when air rises in narrow bands, creating lines of clouds that stretch for miles. They form when wind blows over a surface that is heated unevenly, such as land and water, or when a layer of air becomes unstable and organizes into convection cells. The air rises in some areas and sinks in others, creating alternating strips of clouds and clear sky. From the ground, cloud streets may not be obvious, but from an airplane or satellite, they are striking, like furrows plowed across the sky. They often appear over oceans when cold air flows over warmer water, causing the water to evaporate and feed the rising columns of air. Cloud streets can extend for hundreds of miles, aligning with the direction of the wind. They are a beautiful example of how the atmosphere organizes itself, finding patterns in chaos, creating order from the invisible flows of heat and air. Some clouds are invisible to the naked eye, Subvisual cirrus clouds exist in the upper troposphere, made of ice crystals so sparse that they do not scatter enough light to be seen from the ground. They are detected only by instruments, particularly LiDARs, which use laser light to probe the atmosphere. These invisible clouds are important for climate because they still interact with radiation, trapping heat even though they are too thin to see. They are most common in the tropics, where deep convection lofts moisture to high altitudes. Subvisual cirrus can cover large areas, influencing the energy balance of the atmosphere in ways that are still being studied. Their discovery reminds us that not everything in the sky is visible. The atmosphere holds layers and structures that we can only perceive with technology. Just as the ocean has invisible currents and the Earth has hidden magnetic fields, the sky has unseen clouds, ghosts of moisture that shape our climate from the shadows. Clouds have different textures depending on their composition. Clouds made of small water droplets have a soft, diffuse appearance, with edges that blur into the surrounding air. Clouds made of ice crystals are often sharper and more defined, with edges that catch the light and shimmer. Mixed-phase clouds, containing both water and ice, have a complex texture, with some areas smooth and others fibrous. The texture of a cloud can reveal information about the conditions inside it. Smooth clouds suggest stable air and uniform droplet sizes. Ragged or turbulent clouds indicate strong updrafts or wind shear. Mammatus and other unusual textures form when air is sinking or mixing in complex ways. Even from the ground, careful observation of cloud texture can tell you something about the atmosphere. Is the air stable or unstable? Is the cloud growing or dissipating? Is it likely to produce precipitation? The sky is written in textures, and clouds are the script. Clouds have cultural and spiritual significance in many traditions. Native American traditions often see clouds as messengers or spirits, carrying the voices of ancestors. In Chinese culture, clouds represent good fortune and are often depicted in art alongside dragons and other auspicious symbols. The Maori of New Zealand have a word, kapua, for cloud, and their mythology includes stories of cloud beings who interact with the human world. Across cultures, clouds have been seen as liminal spaces, places between earth and sky, between the known and the unknown. They are transient, appearing and vanishing without warning. They are vast, beyond human control. They are life-giving, bringing the rain that sustains crops and rivers. To look at clouds is not just a scientific act. It is a human act, connecting us to thousands of years of people who have looked up and wondered. Clouds can form in the absence of moisture from the surface. Sublimation, the process by which ice turns directly into vapor without melting, can provide moisture to the atmosphere even in cold, dry regions. This is how clouds sometimes form over polar ice caps or high-mountain glaciers. The ice releases water vapor into the air, which then rises and condenses at higher altitudes, forming clouds without any input from liquid water. These clouds are often thin and fleeting, but they play a role in the energy balance of polar regions by reflecting sunlight and trapping heat. Sublimation also works in reverse. In extremely cold clouds, water vapor can deposit directly onto ice crystals, causing them to grow without passing through the liquid phase. This is the Bergeron-Findeisen process, which is essential for the formation of snow and other frozen precipitation. It shows that water does not need to follow the simple path of liquid to vapor to liquid. It can take shortcuts, skipping phases depending on temperature and pressure. Clouds are flexible systems, adapting to whatever conditions the atmosphere provides. Cloud shadows are visible from space. When sunlight strikes a cloud, Some of the light is reflected, but the cloud also casts a shadow on the surface below or on other clouds nearby. These shadows can be seen from satellites as dark patches on the Earth or as darker regions in layered cloud systems. From the ground, cloud shadows move across the landscape, creating shifting patterns of light and dark. On a partly cloudy day, you can watch these shadows race over fields, forests, and buildings, changing the appearance of everything they touch. Animals often respond to cloud shadows, mistaking them for predators or using them to find shelter from the sun. Cloud shadows also affect temperature. When a shadow passes over, the ground cools slightly, and when it moves away, the warmth returns. In deserts or open plains, where the sun is intense, these fleeting patches of shade can be a relief. Cloud shadows are reminders that clouds are not just objects in the sky. They interact with the world below, shaping light, temperature, and even behavior. The study of clouds is called nephology. It is a branch of meteorology focused on understanding cloud formation, classification, dynamics, and their role in weather and climate. Nephologists use a variety of tools, from simple visual observation to satellite imagery, radar, LiDAR, and computer models. They study how clouds form in different environments, how they interact with radiation, how they produce precipitation, and how they might change as the climate warms. Cloud research is challenging because clouds are complex, multi-scale phenomena. A single cloud can contain processes happening at the scale of micrometers, such as droplet formation, and at the scale of kilometers, such as convection and wind shear. Models must represent both scales accurately, which requires enormous computational power. Despite these challenges, cloud science has advanced rapidly in recent decades. We now understand far more about cloud microphysics, cloud aerosol interactions, and the role of clouds in the climate system than we did 50 years ago. But there is still much to learn. Clouds remain one of the largest uncertainties in climate projections, a humbling reminder that even the most familiar features of the sky can be deeply mysterious. Clouds can affect your mood. Grey, overcast skies are often associated with feelings of sadness or lethargy. This is partly due to the reduction in sunlight, which affects the production of serotonin, a neurotransmitter that influences mood. People who are sensitive to light may experience seasonal affective disorder during prolonged periods of cloudiness, especially in winter. But clouds can also have positive effects. For some people, cloudy weather feels cozy and calming, a reason to slow down and relax. The sound of rain on a roof can be soothing. The diffuse light of an overcast day can be easier on the eyes than harsh sunlight. And the dramatic beauty of storm clouds, sunsets, or rare cloud formations can inspire awe and wonder. The relationship between clouds and mood is personal and varies from person to person. Some people thrive in sunny climates, while others prefer the softness of cloudy days. Regardless of preference, clouds shape our emotional landscapes, just as they shape the physical sky. In the end, clouds are paradoxes. They are fragile yet powerful, transient yet essential. Simple in concept, yet infinitely complex in detail. They are made of the lightest material, yet they hold the weight of the world's water cycle. They are invisible processes made visible, the breath of the earth rendered in forms we can see. They are both the stage and the actors in the drama of weather, shaping what happens below while being shaped by it in turn. They connect the oceans to the land, the surface to the stratosphere, the past to the future. They are ancient, older than any human civilization, yet they are born anew every moment. They are local, forming over specific hills and valleys, yet they are global, part of a system that spans the entire planet. To study clouds is to study the atmosphere itself, to learn how energy, water, and motion interact to create the world we experience. To watch clouds is to practice patience, to accept change, to find beauty in impermanence. They remind us that nothing lasts forever, but that new forms are always emerging, always dissolving, always beginning again. The speed at which clouds move varies dramatically across the sky. Near the surface, stratus and stratocumulus clouds might drift at 5 to 15 miles per hour, moving slowly enough that you can watch their gradual progress across the horizon. Middle-level clouds like altocumulus typically travel faster, pushed by winds that increase with altitude, moving at 20 to 30 miles per hour. But high cirrus clouds can race across the sky at speeds exceeding 100 miles per hour, carried by the jet stream. From ground, these high clouds appear to move slowly because of their great distance. But if you watch carefully for several minutes, you can see them streaming across the heavens like rivers of ice. The jet stream itself is a ribbon of high-speed wind that flows from west to east across the middle latitudes, typically between 25,000 and 40,000 feet. It meanders north and south, creating patterns that steer weather systems. Clouds caught in the jet stream are passengers on this invisible highway, traveling vast distances in a single day. Clouds sometimes form perfect geometric patterns. Under specific conditions, convection cells in the atmosphere can organize into hexagonal shapes, creating what are called cloud cells. From above, these appear as honeycomb patterns, with rising air in the centers and sinking air at the edges, or sometimes the reverse. These patterns occur most often over oceans, where the surface temperature is uniform, allowing the atmosphere to organize itself into regular structures. The phenomenon is related to Rayleigh-Bernard convection, the same physics that causes patterns in heated fluids. Similar patterns can be seen in laboratory experiments with oil or water heated from below. In the atmosphere, the scale is enormous, with individual cells spanning miles across. Satellite images reveal these patterns regularly, particularly in the trade wind regions, where steady winds and warm water create stable conditions. The sight of clouds organized into perfect geometry is a reminder that the atmosphere, despite its seeming chaos, follows mathematical rules. Beneath the randomness is order, patterns waiting to be revealed. Clouds can weigh millions of tons, yet never fall from the sky. A single large cumulonimbus cloud, the kind that produces thunderstorms, can contain 500 million kilograms of water. That is roughly the weight of 100,000 elephants. Yet this enormous mass stays aloft because it is distributed among countless tiny droplets, each suspended by updrafts that move faster than the droplets can fall. The average terminal velocity of a cloud droplet is about 1 centimeter per second, so slow that even a gentle breeze can keep it airborne. Only when droplets merge together into larger drops through collision or ice crystal growth do they become heavy enough to overcome the updrafts and fall as rain. This process takes time, which is why clouds can exist for hours without producing precipitation. The cloud is not static. Water is constantly evaporating from droplets that move into drier air, and new droplets are constantly forming where air rises and cools. The cloud is a dynamic equilibrium, a balance between formation and dissipation, between rising and falling. Some clouds form rings around mountains. Banner clouds are formations that appear on the lee side of a mountain peak, streaming away from the summit like flags. They form when wind flows over the mountain and creates a vortex of low pressure on the downstream side. Air spirals in this vortex, cools and condenses, creating a cloud that appears attached to the peak. The Matterhorn in Switzerland is famous for its banner cloud, which often makes the mountain look as though it is smoking. Banner clouds are stationary relative to the mountain, even though wind flows through them continuously. They are similar to lenticular clouds, but form in a slightly different way, driven by the aerodynamics of the peak itself. Climbers and mountaineers watch banner clouds carefully, because their presence and behavior can indicate wind conditions at the summit. A large, active banner cloud suggests strong winds that could make climbing dangerous. These clouds are mountain ornaments, nature's way of adorning peaks with flowing, ever-changing decoration. Clouds can create their own weather systems. In tropical regions, particularly over warm oceans, clouds organize into systems called convective clusters. Individual cumulonimbus clouds form in the morning, triggered by solar heating. As the day progresses, these clouds grow and merge, creating larger systems. By afternoon, a cluster of thunderstorms may cover hundreds of square miles, producing heavy rain, lightning, and strong winds. The process is self-reinforcing. Rising air in one storm creates low pressure at the surface, which draws in moist air from surrounding areas, fueling more storms. The release of latent heat as water vapor condenses adds energy to the system, strengthening the updrafts. In some cases, these convective clusters can organize into even larger systems, such as tropical storms or hurricanes. The transformation from a simple cloud to an organized weather system happens through feedback loops, where each process amplifies the next. Clouds do not just respond to the atmosphere, they shape it, creating their own environments, building structures that can span entire ocean basins. Clouds contain liquid water, even at temperatures far below freezing. This phenomenon, called supercooling, occurs when pure water remains liquid despite being colder than its normal freezing point. In clouds, water droplets can cool to -40 degrees Celsius or lower without freezing, as long as they remain pure and undisturbed. The reason is that freezing requires a nucleus, a surface for ice crystals to form on. Without particles to trigger crystallization, water molecules remain in a liquid state, unable to organize into the rigid structure of ice. But supercooled water is unstable. The slightest disturbance can cause it to freeze instantly. When an aircraft flies through a cloud of supercooled droplets, the drops freeze on contact with the wings and fuselage, building up ice rapidly. This is one of the most dangerous forms of icing for aviation. Eventually, supercooled clouds do freeze, either through collision with ice crystals that fall from above or through spontaneous nucleation when temperatures drop low enough. Process transforms the cloud, changing its appearance, its ability to reflect light, and its behavior in producing precipitation. Clouds have been observed interacting with solar eclipses. During a total solar eclipse, when the moon passes between the Earth and the Sun, the sudden drop in light and temperature can affect clouds. Some clouds dissipate as the cooling air becomes more stable and can no longer support condensation. Others thicken as the rapid temperature change creates new patterns of rising and sinking air. The shadow of the moon races across the landscape at supersonic speeds, and sensitive instruments have detected changes in cloud properties as the shadow passes. Some observers have reported seeing clouds change color or texture during totality, though these effects are subtle and difficult to distinguish from changes in the observer's perception as light levels drop. Solar eclipses are rare opportunities to study how clouds respond to rapid changes in solar radiation, providing insights into the sensitivity of cloud formation to small perturbations in the atmosphere. They are also moments when the sky becomes briefly unfamiliar, when even the clouds seem to acknowledge the cosmic event unfolding above. Clouds can preserve ancient air. Ice cores drilled from glaciers and polar ice sheets contain bubbles of air trapped thousands of years ago. Some of this air was part of clouds before it became locked in ice. When water vapor condenses into snow that falls on a glacier, it brings with it traces of the atmosphere at that moment. Over time, as more snow accumulates, the layers compress into ice, sealing the air bubbles. Scientists extract these cores and analyze the gases inside, reconstructing the composition of the atmosphere in the distant past. They can measure carbon dioxide levels from before the Industrial Revolution, track changes in methane, and even detect volcanic eruptions through the presence of sulfur compounds. Clouds are part of this archive. Every snowflake that fell was once a cloud droplet, and every droplet carries information about temperature, humidity, and atmospheric chemistry. In this way, clouds are not just transient phenomena. They are recorders of history, writing their data in ice that can be read millennia later. Clouds can split sunlight into crepuscular rays. These are the beams of light that appear to radiate from the sun when it is partially hidden behind clouds, or when dust and haze scatter light in specific ways. The rays are actually parallel, but perspective makes them appear to converge toward the sun, like the spokes of a wheel. They occur when clouds create shadows in the atmosphere, blocking some of the sunlight while allowing other rays to pass through gaps. The contrast between lit and shadowed air makes the rays visible. Crepuscular rays are most dramatic near sunrise or sunset, when the low angle of the sun casts long shadows and the light is warm and golden. Sometimes, rays can be seen extending all the way across the sky, converging again at the anti-solar point opposite the sun. These are called anti-crepuscular rays, and they create the illusion of light beams stretching from horizon to horizon. Both types of rays are optical effects, tricks of perspective and scattering, but they transform the sky into something cathedral-like, as if the clouds have opened windows for light to pour through. Clouds can form underground. In caves with high humidity and stable temperatures, water vapor can condense into fog or mist, creating clouds that fill the cavern. These underground clouds occur most often in limestone caves, where water seeps through the rock, evaporating and saturating the air. The process is the same as cloud formation in the atmosphere, but confined to the enclosed space of the cave. Some caves have permanent clouds that hover near the ceiling or drift through chambers like ghosts. Explorers describe walking through these clouds, feeling the cool moisture on their skin, hearing the echo of their footsteps muffled by the dense air. Underground clouds are rare and require specific conditions, but they remind us that cloud formation is not unique to the open sky. Wherever air, water vapor, and cooling come together, clouds can form, even in the hidden spaces beneath the earth. Clouds can produce sounds beyond thunder. The collision of ice particles inside a cloud creates faint crackling and hissing, though these sounds are rarely heard from the ground. In strong updrafts, the turbulence generates a low roar, similar to the sound of a waterfall or a strong wind through trees. This noise is most intense inside the cloud itself, where air moves at high speeds and water droplets and ice crystals collide constantly. Pilots who fly through cumulonimbus clouds report the deafening din of the storm, a combination of wind, impact, and the vibration of the aircraft itself. On the ground, we hear only the thunder, the shock wave of lightning traveling through the air. But the cloud is never silent. It is a noisy place, full of motion and collision, a hidden symphony that we are shielded from by distance and the absorbing effect of the water droplets themselves. The sounds of clouds are part of the hidden architecture of weather, processes that happen constantly but remain beyond our perception unless we venture into the heart of the storm. Clouds can create mirages in the sky. Fata Morgana is a complex form of mirage that occurs when layers of air at different temperatures bend light in unusual ways, causing distant objects to appear distorted, inverted, or elevated. Clouds can participate in these mirages, appearing to float higher or lower than they actually are, or taking on distorted shapes that shift and waver. The phenomenon is named after Morgan Le Fay, a sorceress from Arthurian legend, because the mirages were thought to be magical illusions. Fata Morgana mirages are most common over cold surfaces like ice or water, where temperature gradients are strong and stable. They can make distant ships appear to hover above the horizon or cause mountains to loom larger than they are. When clouds are involved, the effect can be especially surreal, with cloud layers stacking in impossible configurations or appearing to merge with the ground. These mirages are optical effects, entirely real in the sense that the light is genuinely being bent by the atmosphere, but illusory in that what you see does not match the actual location or shape of the objects. They are reminders that the atmosphere is not just a passive medium, it is an active participant in shaping what we see. Clouds can form chains across the sky. When conditions are right, convection can organize into lines rather than scattered puffs. These cloud lines, sometimes called cloud streets when they are parallel, can extend for hundreds of miles. They form when wind blows perpendicular to a series of updrafts and downdrafts, creating alternating strips of rising and sinking air. Clouds form where air rises, and clear sky appears where air sinks. The result is a pattern of parallel bands that march across the sky like furrows in a field. Cloud streets are common over tropical oceans, where the trade winds create steady conditions that favor organized convection. They are also seen over lakes and coastal areas, where temperature differences between land and water set up circulation patterns. From an airplane, cloud streets are a beautiful sight, proof that the atmosphere is not random but structured, following rules of fluid dynamics that create order on a grand scale. Even something as simple as a line of clouds reveals the complexity of the air we live beneath. Clouds can affect plants through a phenomenon called cloud-water interception. In tropical mountain forests and coastal regions, low clouds and fog often envelop the vegetation for hours or days at a time. Water droplets from the clouds settle on leaves, bark, and needles, where they coalesce and drip to the ground. This process, called fog drip or occult deposition, can provide significant amounts of water to ecosystems, sometimes as much as or more than rainfall. In some regions, forests depend on cloud water to survive dry seasons. The trees themselves can shape the clouds, creating conditions that encourage condensation. Tall trees act as obstacles that force air upward, cooling it and wringing out moisture. In this way, forests and clouds engage in a partnership. The forest creates the conditions for clouds to form, and the clouds provide the water that the forest needs to grow. The relationship is delicate. When forests are cleared, cloud formation can decrease, reducing the water supply and making the land drier. This feedback loop is one reason why deforestation can have such profound effects on local climates. Clouds sometimes produce glories, colorful rings that appear around the shadow of an observer. Glories are most often seen from aeroplanes, where the shadow of the aircraft falls on a cloud below, surrounded by concentric circles of color. The effect is caused by light scattering backward from the cloud droplets, a process called backscattering. The size and spacing of the rings depend on the size of the droplets, making glories a diagnostic tool for cloud properties. Unlike rainbows, which are caused by refraction inside water drops, glories are caused by diffraction and interference around the drops. The physics is complex, involving wave interactions that occur when light waves overlap and combine. Glories are personal phenomena. Each observer sees their own glory, centered on their own shadow, because the scattering occurs at specific angles relative to the light source and the observer. From the ground, glories can sometimes be seen on fog or mist, particularly from mountains where you can look down on a cloud layer with the sun behind you. They are called Brocken spectres when combined with the magnified shadow of the observer, a phenomenon named after a peak in Germany where the effect is frequently observed. Clouds can seed the formation of other clouds. When a cumulus cloud evaporates, it leaves behind cooled air and increased humidity in the region where it existed. This can make it easier for new clouds to form nearby, as the air is closer to saturation and requires less additional cooling to condense. Similarly, the outflow from a thunderstorm, the cool air that rushes out from beneath the storm, can trigger new convection when it collides with warm, moist air. This process can create lines or clusters of storms that propagate across a region, each storm triggering the next. The life cycle of clouds is interconnected. Individual clouds rise, mature, and dissipate, but they leave legacies in the atmosphere that influence what comes after. Cloud formation is not just a response to current conditions. It is shaped by the history of clouds that came before, by the moisture they released, the cooling they caused, and the patterns of rising and sinking air they created. The sky is not a blank slate. It is a palimpsest, written and rewritten by generations of clouds. Clouds can be dated using satellite data. By tracking clouds across multiple images taken minutes or hours apart, scientists can determine their age, their speed, and their direction of movement. Young clouds are typically bright and compact, with sharp edges and strong vertical development. As they age, they spread and flatten, their edges become ragged, and their internal structure weakens. Tracking cloud evolution helps meteorologists understand storm development and predict when new cells will form. It also provides data for validating computer models, which must simulate cloud life cycles accurately to forecast weather correctly. The ability to watch clouds evolve in real time from space is a relatively recent development. Early weather satellites took images every few hours, providing snapshots but not continuous observation. Modern geostationary satellites orbit at a fixed point above the Earth, capturing images every few minutes and allowing clouds to be tracked continuously. This time-lapse view of the atmosphere reveals patterns that were invisible before, showing how clouds organize, merge, split, and dissipate in a constant dance. Clouds can create acoustic phenomena beyond thunder. In some thunderstorms, observers have reported hearing low-frequency rumbles that precede or follow lightning by several seconds. These sounds may be caused by the movement of air within the cloud, by the collision of ice particles, or by pressure waves generated during the storm's development. The exact mechanisms are still being studied. Another acoustic effect involves the way clouds modify the propagation of sound. A low cloud layer can trap sound waves, creating a duct that allows sounds to travel farther than they would under clear skies. This is why distant trains, highways, or industrial noise can sometimes be heard more clearly on cloudy nights. The clouds act as a ceiling that reflects sound waves back toward the ground, preventing them from escaping upward. Conversely, certain cloud configurations can absorb sound, making the environment quieter. The relationship between clouds and sound is subtle and often unnoticed, but it shapes the acoustic landscape we experience, influencing what we hear and how far sounds travel. Clouds can interact with the Earth's magnetic field. Water droplets and ice crystals are electrically neutral under normal conditions, But in thunderstorms, the collision of particles generates static electricity, separating positive and negative charges. This process creates electric fields strong enough to influence the behavior of the cloud itself. The electric field can orient ice crystals, causing them to align in specific directions. It can also affect the growth of droplets, as charged particles attract or repel each other. Some research suggests that the Earth's magnetic field may play a role in cloud formation by influencing cosmic rays, high-energy particles from space that penetrate the atmosphere. When cosmic rays collide with air molecules, they create ions, which can act as condensation nuclei for cloud droplets. The intensity of cosmic rays varies with the Sun's magnetic activity and the Earth's magnetic field, potentially linking solar cycles to cloud cover and climate. This hypothesis is controversial and still being tested, but it represents an intriguing possibility that clouds are influenced not just by local weather, but by forces that originate in the Sun and the broader cosmos. Clouds can produce light shows beyond lightning. Ball lightning, a rare and poorly understood phenomenon, consists of glowing spheres that appear during thunderstorms. These balls of light hover or move slowly, sometimes passing through walls or windows, and can last for seconds or minutes before disappearing. Witnesses describe them as ranging in size from golf balls to beach balls, glowing in various colors, and sometimes emitting sounds or smells. Despite numerous reports, ball lightning has never been reliably captured on film or recreated in a laboratory, making it one of the great mysteries of atmospheric physics. Some scientists propose it is a form of plasma. Others suggest it involves electromagnetic fields or chemical reactions. The connection to clouds is clear, as ball lightning occurs almost exclusively during thunderstorms, but the exact mechanism remains elusive. Other light phenomena associated with clouds include sprites, jets, and elves, which are brief flashes of light that occur high above thunderstorms, reaching into the mesosphere. These transient luminous events were only discovered in recent decades, as cameras became sensitive enough to capture them. They reveal that thunderstorms extend their influence far beyond the troposphere, creating effects that ripple through the entire atmosphere. Clouds have inspired technological innovations. The first cloud chambers, devices used to detect subatomic particles, were named after clouds because they worked on the same principle. A chamber filled with supersaturated vapor would form tiny droplets along the trails of ionizing particles, making their paths visible. This invention helped physicists discover and study particles like electrons and muons, leading to breakthroughs in quantum mechanics and nuclear physics. Cloud computing, the modern technology for storing and processing data over the internet, borrowed its name from the way clouds seem to be everywhere and nowhere, accessible from any location, but not tied to a specific place. Cloud-inspired architecture uses diffuse, layered structures to distribute light or air, mimicking the way clouds scatter sunlight. Even the concept of brainstorming, generating ideas freely and openly, is sometimes called blue sky thinking, evoking the open, limitless feeling of a clear sky with just a few inspiring clouds. Clouds are more than meteorological phenomena. They are metaphors, models, and sources of inspiration for how we think about complexity, connection, and creativity. Clouds can form in the wake of ships. Ship tracks are long, narrow clouds that appear over oceans, trailing behind vessels for miles. They form when exhaust from the ship's engines releases particles into the air. These particles act as cloud condensation nuclei, allowing droplets to form in air that is near saturation, but lacks enough natural nuclei to condense. The result is a cloud that follows the ship's path, often visible from satellites as a white line cutting through a layer of marine stratocumulus. Ship tracks are a form of inadvertent weather modification, a demonstration that human activities can influence cloud formation on a local scale. They also provide a natural experiment for studying cloud aerosol interactions. By comparing the properties of ship-track clouds to the surrounding natural clouds, scientists can learn how particle concentration affects droplet size, cloud reflectivity, and lifetime. Some research suggests that the increased reflectivity of ship-track clouds could have a cooling effect on the climate, though the overall impact is small compared to other factors. Ship tracks are visible reminders of the interconnection between human activity and atmospheric processes, showing that even routine operations like shipping can leave marks in the sky. Clouds can form signatures that reveal the landscape below. In satellite images, certain cloud patterns correspond to features on the Earth's surface. Islands can create cloud plumes as wind flows around them, forming von Karman vortices that spiral downwind in beautiful symmetrical patterns. Mountain ranges create bands of clouds on their windward sides and clear areas on their leeward sides, marking the location of peaks even when the mountains themselves are hidden beneath the clouds. Urban areas can influence clouds through the heat island effect, where cities are warmer than surrounding rural areas, creating local updrafts that trigger cloud formation. Some cities have their own characteristic cloud patterns, with cumulus clouds forming preferentially over the warm concrete and asphalt. By studying these cloud signatures, scientists can learn about surface conditions, wind patterns, and the interaction between the land and the atmosphere. Clouds are not isolated. They are shaped by everything beneath them, carrying fingerprints of the terrain, the vegetation, the temperature, and even the activities of the life below. Clouds have been used as clocks and calendars by cultures around the world. In the Pacific Islands, navigators used clouds to locate land beyond the horizon. Stationary clouds that form over islands in the trade winds, called tava in Polynesian languages, can be seen from tens of miles away, guiding sailors to land they cannot yet see. In East Africa, the arrival of specific cloud patterns signals the start of the rainy season, a crucial event for agriculture. Farmers plant their crops when they see the first towering cumulus clouds building over the highlands, knowing that rain will follow within days. In the Arctic, indigenous peoples watch clouds for signs of weather changes, interpreting subtle variations in color and movement to predict storms or clear periods. These traditional knowledge systems, developed over thousands of years, are remarkably accurate and often more nuanced than modern forecasts for specific local conditions. They represent a deep engagement with the sky, a literacy in cloud language that is passed down through generations. In a world increasingly mediated by technology, these practices remind us that observing clouds directly, with our own eyes and accumulated experience, remains a powerful way to understand and anticipate the weather. Clouds can create privacy in the digital age. The term cloud cover has taken on a new meaning in the context of internet privacy and security. Just as physical clouds can hide the sun or the stars, digital cloud systems can obscure data, making it harder to trace or access without proper authorization. This metaphor extends to the way clouds in the sky provide shelter or concealment, a theme that appears in literature and art across cultures. Clouds hide mountains, they hide the moon, they hide the horizon. They create uncertainty, mystery, and the potential for surprise when they part to reveal what was hidden. In an era where transparency and surveillance are constant concerns, the cloud as a metaphor for concealment and protection carries weight. We store our data in the cloud, trusting it to keep our information safe yet accessible. We look to the clouds for cover from the sun's intensity. We find in them a balance between exposure and protection, between connection and privacy. The cloud is a shapeshifter, a boundary that is both barrier and bridge. Clouds are intergenerational teachers. Children learn to identify clouds in school, practicing the names of cumulus, stratus, and cirrus. They draw them in art class, watch them during recess, and dream beneath them at night. Elders remember clouds from their youth, particular storms or sunsets that marked important moments. They pass down weather lore, teaching the young to read the sky as their ancestors did. Clouds connect us across time, offering a shared experience that transcends technology and culture. A cloud seen today is made of the same processes that formed clouds 1,000 years ago, or 10,000. The water in them has cycled through the atmosphere for billions of years, falling as rain, evaporating from oceans, condensing again. That water has been part of countless clouds, each one unique, yet all following the same fundamental patterns. When we watch clouds, we participate in an ancient practice, one that links us to every human who has ever looked up and wondered. Clouds are inheritance and legacy, a gift we receive from the past and pass to the future, unchanging in essence, yet eternally new in form. Clouds remind us of impermanence in a world that often seeks to freeze moments. We try to capture them in photographs, but the image never quite holds the experience of watching them move, of feeling the light change as they pass overhead. We try to name them, to categorize and classify, but every cloud is a gradient, a transition between types that resists clean boundaries. We try to predict them, to model their formation and behavior, yet they continue to surprise us, forming in unexpected places, dissipating when they should persist, producing rain when forecasts called for dry skies. Clouds teach humility. They remind us that no matter how much we learn, nature holds complexity beyond our complete understanding. They invite us to appreciate without possessing, to observe without controlling. In a fast-paced world, clouds move at their own pace, neither hurrying nor waiting. They are neither here nor there, neither solid nor empty, neither permanent nor entirely gone. They exist in the in-between, in the spaces where categories blur, where certainty gives way to mystery. They are, perhaps, the most honest feature of the sky, showing us that change is constant, that beauty is fleeting, and that some things are meant to be watched rather than held. Clouds are companions in solitude. When you are alone, looking up at the sky, clouds keep you company. They change slowly enough that you can watch them, fast enough that they never bore. They make patterns that your mind can interpret, shapes that spark imagination without demanding analysis. They ask nothing of you, offer no judgment, require no response. They simply exist, doing what clouds do, while you do what you do, which is watch and breathe and be. In moments of stress or sadness, clouds can offer perspective. Your troubles feel smaller beneath the vast dome of the sky, where clouds come and go, where storms brew and clear, where sunlight always returns. In moments of joy, clouds amplify the feeling, adding drama or softness to the scene, framing the moment with textures and colors that make it memorable. Clouds are universal, yet personal. Everyone sees them, but no one sees them exactly the same way. The cloud you notice, the shape you find in it, the feeling it evokes, all of that is yours alone, a private experience in a public sky. Clouds are proof that beauty does not need to be rare to be profound. They appear every day, yet they never become ordinary. They are the accessible sublime, the everyday extraordinary, the constant reminder that wonder is always available if we only look up. Cloud watching has become a recognized practice for mindfulness and meditation. The act of observing clouds encourages present moment awareness, pulling attention away from worries about the past or future and anchoring it in the here and now. The slow movement of clouds provides a focal point that is neither too engaging nor too boring, making it ideal for calming an active mind. Unlike some meditation practices that require closing your eyes or sitting in specific positions, cloud watching can be done anywhere there is a view of the sky. You can lie on your back in a field, sit on a bench in a park, or look out a window from your home. The practice has therapeutic benefits. Studies have shown that spending time outdoors observing natural phenomena reduces stress, lowers heart rate, and improves mood. The soft, diffuse light of a cloudy day is easier on the eyes than harsh sunlight, creating a gentler visual environment. The unpredictability of clouds, the fact that you never know quite what shape will appear next, keeps the mind gently engaged without overwhelming it. Cloud-watching organizations, like the Cloud Appreciation Society, have formed around the world, bringing together people who find joy and peace in observing the sky. Clouds can help us understand time and change. The life cycle of a cloud, from formation to dissipation, is a miniature lesson in impermanence. A cumulus cloud might last 30 minutes, forming as a small puff, growing into a towering structure, then dissolving back into invisible vapor. Watching this process unfold teaches patience and acceptance. The cloud was not there, then it was gone. Nothing we did influenced it. We were simply witnesses to a natural cycle. This rhythm of formation and dissolution mirrors larger patterns in life. The way relationships begin and end, the way projects start and finish, the way seasons change and years pass. Clouds show us that endings are not failures. They are natural completions, necessary for new beginnings. When a cloud dissipates, it does not disappear. The water returns to vapor, ready to condense again elsewhere. Energy transforms but does not vanish. The process continues, endless and self-renewing. In a culture that often fears change and clings to stability, clouds model a different way of being, one that embraces transformation as fundamental rather than threatening. Clouds can serve as indicators of air quality. On days when the air is clean and free of pollution, clouds have sharp, well-defined edges. The droplets are uniform in size, creating distinct boundaries between the cloud and clear air. But when pollution is high, clouds become hazier. Aerosols increase the number of cloud condensation nuclei, creating more droplets that are smaller on average. These smaller droplets scatter light differently, making clouds appear brighter and whiter, but also less defined. The edges blur, and the overall texture becomes smoother. In heavily polluted areas, clouds may take on a yellowish or brownish tint from the particles suspended in them. Observing clouds can thus provide a rough sense of air quality. Clear, crisp clouds suggest clean air. Hazy, indistinct clouds suggest higher levels of particulates. This is not a replacement for scientific monitoring, but it is a reminder that the sky reflects what we put into the atmosphere. Clouds are not separate from us. They are shaped by our actions, by the emissions from our vehicles and factories, by the dust we kick up and the chemicals we release. They carry the signature of human influence, visible to anyone who knows how to read it. Clouds can create false horizons and disorient travelers. Pilots sometimes experience whiteout conditions when flying through or above clouds, where the separation between sky and ground becomes impossible to discern. Everything appears white and featureless, with no reference points to indicate up or down. This can lead to spatial disorientation, a dangerous situation where the pilot loses track of the aircraft's attitude and position. Sailors encounter similar phenomena when fog or low clouds merge with the sea, creating a grey void where water and air blend seamlessly. Without a visible horizon, navigation becomes challenging and depth perception fails. Hikers and climbers in mountains can also experience disorientation when clouds descend and visibility drops to a few feet. Landmarks disappear, trails become uncertain, and the sense of direction falters. In these situations, clouds are not just weather. They are obstacles, challenges that test skill, judgment, and sometimes courage. They remind us that the atmosphere is not just scenery. It is an active environment that can help or hinder, reveal or conceal, depending on conditions and circumstances. Clouds can produce snow from clear skies. In very cold conditions, ice crystals can fall from high cirrus clouds that are so thin they are nearly invisible. The crystals drift slowly downward, taking hours to reach the ground. During their descent, they pass through air that is often clear and dry, giving the impression that snow is falling from an empty sky. This phenomenon is called diamond dust in polar regions, where it occurs frequently in winter. The tiny crystals shimmer in the sunlight, creating glittering displays that look like stars falling in slow motion. Each crystal is small, often less than a millimeter across, but together they create a delicate veil that catches the light. Diamond dust is not the same as snow from a storm. It is gentle and sparse, accumulating slowly if at all, but it adds to the ice budget of polar regions. It also creates optical effects, such as halos and light pillars, when the crystals are oriented in specific ways. The experience of watching snow fall from a clear blue sky is surreal, a moment when the expected order of weather is suspended and something stranger appears. Clouds can harbor microbial life. Scientists have discovered bacteria, fungi, and other microorganisms living in clouds, suspended in the water droplets or attached to aerosol particles. These microbes are not passive passengers. Some can actively influence cloud properties by acting as ice nuclei, catalyzing the freezing of supercooled water droplets. This biological component of clouds has only begun to be explored in recent years, and it raises intriguing questions. How do these organisms survive the cold temperatures and low nutrient levels of the atmosphere? How did they get there? Carried up by wind from the surface? Or are some species adapted specifically to aerial life? Do they play a significant role in precipitation or climate? Research is ongoing, but it is clear that clouds are not sterile. They are ecosystems, however sparse, where life exists in one of the most extreme environments on the planet. This discovery adds another layer to our understanding of clouds, showing that they are not just physical phenomena, but also biological ones, part of the larger web of life that includes the atmosphere as habitat. Clouds can influence the migration patterns of birds. Many bird species navigate using the sun and stars, so heavy cloud cover can obscure these celestial cues and make navigation more difficult. However, clouds can also provide benefits. They offer cover from predators, particularly for small birds migrating during the day. They can create thermal updrafts that soaring birds use to gain altitude without expending energy. Some species, such as waterfowl, prefer to migrate under overcast skies, possibly because the diffuse light reduces glare and makes it easier to see landmarks below. Radar studies have shown that cloud patterns can channel migrating flocks, funneling birds along paths where visibility is better or where winds are favorable. During storms, birds may shelter in place or take detours to avoid severe weather, guided by their ability to sense changes in air pressure and cloud formation. The relationship between clouds and bird migration is complex, but it underscores that clouds are not just background scenery. They are active elements of the environment that affect behavior, survival, and the movement of life across the planet. Clouds can create acoustic mirages, where sounds appear to come from the wrong direction. Temperature inversions, where a layer of warm air sits above cooler air, can bend sound waves in the same way that they bend light waves in optical mirages. When this happens near clouds, sounds can be reflected or refracted in unexpected ways. A voice from far away might seem close, or a sound from below might appear to come from above. Sailors have reported hearing conversations from distant ships with eerie clarity, as if the speakers were standing nearby. Hikers in mountains have described sounds echoing strangely when clouds lie in the valleys, creating acoustic effects that make distances deceptive. These phenomena are rare and require specific atmospheric conditions, but they illustrate that clouds shape not only what we see, but also what we hear. The atmosphere is a medium for sound as well as light, and clouds, as concentrations of water and variations in temperature, influence how that medium carries acoustic energy. They are unseen conductors of sound, shaping the sonic landscape in ways we usually do not notice. Clouds can be electrified without producing lightning. In some conditions, the electric field within a cloud can become strong enough to cause a glow around pointed objects, such as the masts of ships or the tips of airplane wings. This phenomenon, called St. Elmo's fire, appears as a bluish or greenish luminescence and is caused by ionization of the air in the strong electric field. It is not dangerous, as no current flows and there is no heat, but it can be startling for those who encounter it. St. Elmo's fire is named after St. Erasmus of Formia, the patron saint of sailors, and has been observed and recorded for centuries. Sailors considered it an omen, sometimes good, sometimes bad, depending on when and where it appeared. The glow can also occur on mountains during thunderstorms, on the horns of cattle, or on any tall, pointed structure exposed to a charged cloud. It is a visible reminder that clouds are electric entities, charged with potential energy that can manifest in ways beyond the dramatic flash of lightning. Clouds can create false rainbows, where the arc appears without rain. These fog bows or cloud bows form in fog or clouds, rather than in rain. Because the water droplets in fog are much smaller than raindrops, the bows they produce are broader and paler, often appearing as white or faintly colored arcs. The small droplet size causes more overlap between the different wavelengths of light, washing out the distinct colors that make rainbows so vivid. Fog bows are most commonly seen in mountain fog or when clouds lie close to the ground. They require the sun to be behind the observer and the fog or cloud in front, just like rainbows. The center of the fog bow corresponds to the anti-solar point, the spot directly opposite the sun from the observer's perspective. Sometimes a fog bow will show faint hints of color at its edges, usually blues and reds, but the overall impression is of a white or silver arc floating in the mist. Fog bows are rarer than rainbows because the conditions must be just right, but they are equally beautiful in their subtlety, a gentle ghost of color in the gray. Clouds can create shadows on other clouds. In layered cloud systems, where different types of clouds exist at different altitudes, higher clouds can cast shadows on lower ones. From an airplane, you can sometimes see the shadow of a cirrus cloud falling across a layer of alto cumulus below, creating dark patches that move as the clouds drift. These shadows can be sharp and defined, or they can be diffuse, depending on the thickness and height of the clouds. They add depth to the sky, making it clear that clouds occupy three-dimensional space rather than lying flat against a blue backdrop. From the ground, Cloud shadows are most noticeable when they fall on other clouds near the horizon, creating contrasts of light and dark that enhance the sense of distance and scale. Shadows remind us that clouds block light, that they have substance and volume, that they are real objects occupying real space. They are not paintings on the dome of the sky. They are structures within the atmosphere, each one existing at a specific altitude, each one casting its own influence on the light that passes through or around it. Clouds can preserve information about past climate conditions. When snow falls on glaciers and accumulates over time, it forms layers that record the history of precipitation. Each layer contains information about the temperature, humidity, and atmospheric composition at the time it fell. Volcanic eruptions leave ash layers that can be identified and dated. Dust from deserts or pollen from plants provides clues about wind patterns and vegetation. Even the chemical composition of the ice itself reveals details about past greenhouse gas concentrations. Ice cores, drilled from Greenland and Antarctica, extend back hundreds of thousands of years, creating a timeline of climate history that includes detailed records of cloud formation and precipitation. By studying these cores, scientists can reconstruct ancient weather patterns, track the evolution of ice ages, and understand how the climate system has responded to natural changes in the past. Clouds, through the snow and ice they produce, are archivists, recording data that allows us to read the climate history of the planet. Clouds sometimes form behind airplanes in ways unrelated to contrails. Wake turbulence, the spiraling vortices of air created by an aircraft's wings, can sometimes trigger cloud formation in moist air. These vortex clouds appear as short-lived spirals or tubes trailing behind the plane, distinct from the linear contrails left by engine exhaust. They form because the vortices create areas of low pressure where air cools and condenses. The effect is most visible when the air is near saturation, so close to forming clouds that the slight cooling induced by the vortex is enough to tip it over the threshold. Vortex clouds are rare and usually dissipate within seconds, but they provide a visible demonstration of how aircraft disturb the atmosphere. They show that even the passage of a plane through the sky leaves ripples, small perturbations that change the air in ways we can sometimes see. The atmosphere is sensitive to these disturbances, and clouds are the indicators that make them visible. Clouds can form in layers so thin they are almost transparent. Cirrostratus clouds can spread across the entire sky as a veil so delicate that the sun or moon shines through with only slight dimming. These thin layers are often barely perceptible, noticed only by the halo they create, or by the slight milkiness they add to the sky. Yet they cover vast areas, sometimes spanning entire regions or continents. From space, they appear as faint, fibrous sheets, almost ghostly in their translucence. Despite their thinness, these clouds affect the Earth's energy balance by trapping infrared radiation and allowing sunlight to pass through. They are evidence that clouds do not need to be thick or dramatic to matter. Even the subtlest layers play a role, contributing to the complex system of heating and cooling that governs our climate. Cirrostratus reminds us that much of what happens in the atmosphere is quiet and unobtrusive, unfolding without fanfare, shaping conditions without calling attention to itself. Clouds can produce rings of light called cloud iridescence at their edges. This phenomenon occurs when thin clouds containing water droplets or ice crystals of uniform size pass near the sun. The sunlight is diffracted by the particles, spreading into its component colors and creating bands of pastel hues along the edge of the cloud. The colors are often delicate, pinks, greens, blues, and purples, shifting and changing as the cloud moves and the viewing angle changes. Cloud iridescence is different from a rainbow or a halo. It is more localized, appearing only in small patches, and it requires the cloud to be thin and the particles to be very uniform in size. The effect is fleeting, lasting only as long as the conditions remain perfect. To see cloud iridescence, you need to be in the right place at the right time, looking at the right cloud with the sun at the right angle. It is one of the sky's small gifts, a reward for paying attention, for looking up at just the right moment. Clouds can be weapons in military strategy. Cloud cover has historically influenced the outcomes of battles by concealing troop movements, protecting forces from aerial observation, or providing cover for aircraft. During World War II, bombers relied on cloud-free conditions for visual targeting, so heavy cloud cover could prevent or delay missions. Conversely, clouds could protect targets from attack, forcing planes to rely on less accurate radar bombing or to abandon missions entirely. Naval battles could be influenced by fog and low clouds, which obscured ships and made it harder to aim artillery. In modern warfare, while satellite and radar technology can see through clouds, weather remains a factor. Cloud cover affects infrared and optical sensors, influences flight conditions, and shapes the decision-making of commanders. Weather modification, including attempts to seed clouds to create rain or fog, has been explored by militaries as a form of environmental warfare, though such tactics are now banned by international treaty. Clouds are not neutral. They are part of the strategic environment, elements that can be exploited or must be overcome. Clouds can affect satellite operations and space weather forecasting. Thick cloud cover can block ground-based observations of satellites, making it difficult to track objects in orbit or to observe events like rocket launches or meteor showers. Satellites themselves must account for clouds in their operations. Earth observation satellites use sensors designed to see through clouds, or to wait for clear conditions before taking high-resolution images. Weather satellites, of course, focus on clouds specifically, using multiple wavelengths to capture data about cloud properties. But clouds can also interfere with communication satellites, particularly when heavy precipitation causes signal attenuation. Rain fade is a common problem for satellite TV and internet, where heavy rain absorbs and scatters radio waves, weakening the signal. Clouds themselves are less of an issue, but the rain they produce can significantly degrade performance. The interaction between clouds and satellites is a reminder that the atmosphere is not just background. It is an active layer that must be navigated, accounted for, and sometimes worked around. Technology has made us less dependent on clear skies, but clouds remain a factor that shapes how we use space. Clouds can evoke specific emotions and memories. The sight of certain cloud formations can trigger nostalgia, recalling childhood afternoons lying in the grass or family trips to the beach where thunderstorms gathered on the horizon. Dark, heavy clouds might bring a sense of foreboding or melancholy, while bright cumulus against a blue sky can lift the spirit and evoke feelings of freedom and possibility. The smell of rain approaching, carried on the wind before the first drops fall, is a powerful sensory trigger that can transport people back to specific moments in their past. Psychologists recognize that weather and clouds are deeply connected to emotional states, not just through direct physiological effects like light exposure, but through associations and memories. The weather of important days becomes part of how we remember them. A wedding under clear skies, a funeral under grey clouds, a first kiss during a summer storm. Clouds are witnesses to our lives, providing the backdrop for countless moments, and their presence or absence colors how we feel and what we remember. Clouds can disappear and reappear in cycles. Certain weather patterns create oscillating conditions, where clouds form and dissipate repeatedly in the same location. For example, morning fog over a valley may clear by mid-morning as the sun heats the ground, then reform in the evening as temperatures drop. Mountain clouds may build in the afternoon as heated air rises up slopes, then vanish at night when the process reverses and cool air drains back down. These cycles create rhythms that define local climates. In tropical regions, afternoon thunderstorms are so regular that you can almost set a clock by them. The heat of the day triggers convection, clouds build, rain falls, and by evening the sky clears. This pattern repeats daily during the wet season, creating a predictable cycle that shapes ecosystems and human activities. Understanding these cycles allows communities to plan around the weather, knowing when roads will be passable, when outdoor work should be done, when to expect rain. Clouds are not random. They follow patterns, and recognizing those patterns provides a sense of order and predictability in an otherwise complex system. Clouds can reveal the invisible structure of the atmosphere. The shapes and arrangements of clouds trace out wind patterns, temperature gradients, and regions of rising or sinking air. A line of cumulus clouds might mark a sea breeze front, the boundary where cool ocean air meets warm land air. A band of clouds along a mountain range reveals where moist air is being forced upward by terrain. Gaps in cloud cover over a valley indicate a rain shadow, where descending air has dried out after crossing a mountain. Satellite meteorologists read clouds the way detectives read clues, inferring the presence of weather systems, jet streams, fronts, and other features that are not directly visible. Clouds are not the atmosphere itself, but they are manifestations of its structure, indicators that reveal what is happening in the invisible ocean of air around us. By learning to read clouds, we gain insight into processes that would otherwise remain hidden, making the intangible tangible, the invisible visible. Clouds can mediate the connection between Earth and space. They are formed by processes on the Earth's surface, evaporation from oceans and transpiration from plants, and they extend upward into the atmosphere, where they interact with sunlight, cosmic rays, and eventually the vacuum of space at the top of the mesosphere. Noctilucent clouds, those rare silver-blue formations in the mesosphere, are at the very edge of where clouds can exist, higher than any weather, in air so thin it barely deserves the name. They mark the boundary between atmosphere and space, a transition zone where earthly processes give way to the realm of satellites and stars. Even lower clouds, the familiar cumulus and stratus of everyday weather, are part of this connection. The water in them came from the ocean, evaporated by the sun, and it will eventually fall back to Earth, completing a cycle that links the surface, the air, and the cosmos. Clouds are not isolated. They are part of the great vertical integration of Earth systems, from the depths of the ocean to the edge of space. In all their forms, clouds are invitations to pause and observe. They are free entertainment, available to anyone with a view of the sky. They ask only that we look up, that we take a moment from whatever occupies us, and that we notice what is happening overhead. In doing so, they pull us out of our concerns and into the present moment. They remind us that we are part of a larger system, that we live beneath a vast, dynamic atmosphere that operates on scales far beyond our individual lives. They offer perspective, beauty, and a sense of connection to the natural world. Clouds are democratic. They do not care about wealth or status or achievement. They appear to everyone equally, offering the same shapes, the same colors, the same gentle motion. In a world that often feels divided and unequal, clouds are a common inheritance, a shared treasure that belongs to no one and everyone. They are the sky's gift, given freely, renewed constantly, always available for those who take the time to look up and receive it. Thank you for floating through the quiet sky with me tonight. As we wandered together from one cloud to the next, we saw how water and air come together to create the forms that shape our weather, our light, and our world. From the highest ice crystals to the lowest fog, from the gentlest stratus to the fiercest cumulonimbus, every cloud is a moment of balance, a fleeting sculpture in the atmosphere. They are not permanent, they are not solid, but they are real and they matter. If you enjoyed this quiet journey through the layers of the sky, I invite you to like, subscribe, or share a thought below. It helps other curious dreamers find their way here, one sleepy soul at a time. But for now, let all that float away. Let your breathing slow. Let your thoughts soften, like a cloud dissolving into clear blue. The sky will keep changing without you for a while. The weather will continue its cycles. The clouds will form and vanish, rise and fall, carrying water from ocean to mountain, from dawn to dusk. You have done enough for today. Close your eyes, rest, and dream of soft horizons. Good night.